Okay. Hello everyone. I'm Asif Ahmad from Agnisys, and I'm here to present our work in the paper titled ML-based verification and regression automation. As we all know that in today's time, verification and validation of designs is a complex and time-consuming process. It requires a lot of manual work. There is so much need to automate, and hence ML can be used to a great extent for automation in this regard. So what are the challenges that we faced in design verification and validation? The framework is complex and time consuming. We need to manually debug the errors and isolate them and verify the waveforms and validate those errors. So ML algorithms can be used in a continuous integration and continuous development cycle to ease the tedious process of verifying and validating these complex design changes. So what we propose in this paper is basically a solution to A, validate text-based regression, B, validate waveforms on simulation. So let's focus on the ML algorithms and techniques that are used in our experiments. So autoencoder is an unsupervised machine learning algorithm that looks for the minimum value of the error function. It basically reduces the size of the inputs into a smaller representation, and the reconstruction loss of the inputs are then produced, and attempt is then made to reconstruct those inputs at the output. So as you can see in the figure, the loss can be calculated using the predicted inputs and outputs. A Siamese network, it uses a lesser amount of data to get better predictions. It has the ability to learn from limited data to produce far accurate and better results. As we can see in the figure, the test data, that is the input data, is fed to the Siamese neural network along with the reference data that is stored in the database to generate a similarity score. The clustering algorithm. So DVCon, that is the density-based spatial clustering of applications with noise algorithm, groups a set of data points in a way such that similar data points are grouped together in an unsupervised neural network. This clustering technique is much more efficient to detect outliers. As we can see in the figure, that the data points represented by the black dots are outliers that lie outside the grouped area. Embedding, it is basically a low-dimensional learned continuous vector representation of discrete variables. It plays an important role in neural networks by mapping tokens to a fixed vector and makes model easier to use. And backpropagation is widely used for the training of the neural networks by calculating the gradient of given loss function with respect to the weights of the neural network. So what is the training strategy that we used? The autoencoder was first trained with pre-trained embeddings over a variety of inputs at certain learning rate with Adam optimizer and root mean square loss function. A Siamese neural network was built having the initial layers same as the autoencoder. Training was done in such a way that with every run, 3 pairs were chosen: the anchor, the positive, and the negative tag. The anchor and the positive tags formed a pair which was like each other, that is similar to each other. And similarly, the anchor and the negative tags formed a pair which were dissimilar. The distance between each pair of the samples in an n-dimensional space, which is known as the Euclidean distance, was used as the calculating distance. So this is the basic architecture that we used. As I have explained all the terms, so you can see the basic idea here is to group similar scenarios in an n number of scenarios. So what we basically did, that is embedding in the input text to report them as vector forms, these can basically learn while on training. Then convolutional 1D is then used to support parallelism. It has large number of pillars filter with basically much less number of parameters, making it fast for computation. The max pooling layer acts as a downsampling layer for input to reduce its size. Then again, convolutional 1D layer is used, and the flatten layer is later on used to unravel inputs to convert its size into a single dimension. We then concatenate the inputs, and dense layer is used to transform the inputs in a given number of units. And then again, the concatenation is done of the inputs. Focusing on the very first part, that is the text-based regression mechanism, in a CI/CD cycle, code changes are very frequent. That may be due to fixing of some bugs or making some enhancements, improvements, etc. So in order to track the expected output changes, the latest generated output is compared with the previously generated output, or namely the golden output. These changes are in large numbers and most of the time are same and repeated throughout the regression test cases. So the data that we considered for this experiment, a sample of around 1500 scenarios was taken for the initial breakthrough. The CI/CD program involving code changes led to changes in outputs of those scenarios. We then compared the existing output, that is the golden output, with the newly generated output in an aligned way. The differences were then extracted between the two files along with their context. So the method that we use, that all the differences were then dumped and fed to the Siamese model to produce a vector of 1 cross 100 dimension in batches. Clustering algorithm was then applied to form groups which were dumped in the form of text. So on evaluating, we verified with our internal regression environment at Agnisys, and while validating the differences, we could see that an appreciable number of groups with almost same or let's say identical differences were being created. Around 50% of total diffs in the total scenarios were able to form groups, and where each group had at least 5 or more diff members. These are the examples of some created diff groups. So here the bullets 0, 1, and 2 and basically give the information about the diff members, and this is a diff group. Here we can see that the line in the right side code, that is the colon code, with an attribute count is subtracted in the newly generated code. This is another example where we can see the line between the two dotted lines had a difference where the value, hex value, has changed as compared to the colon output. So what are the limitations? Absence of structural information of the generated output text, drastic improper alignment of files sometimes while comparing golden and the newly generated files, and lack of a GUI interface for efficient and visually pleasing mechanism in order to create a relation with the source code with differences in the compared files. Coming to the second experiment, that is the transaction-based wave diff mechanism, it involved a creation of transaction-based intermediate log through some assumptions or user-given data at the initial phase. We then grouped and categorized the transactions with a timestamp to monitor changes in the revised design with respect to the golden design. So the data that we considered, simulation was done on some sample designs, and the value change dump files were dumped. Some tweaks were then later made in the same design, such as adding delays, inserting or deleting some transactions, left shifting or right shifting some transactions with respect to timestamp, etc. VCD files were then converted in a single time relation table. Assumptions were considered to create the intermediate logs, as said earlier, but time gaps were filled with tokens. This is a sample processed VCD data. So we created an intermediate log with the previously shown sample processed VCD data, where transactions were identified through some assumptions and the occurring timestamp, creating a log for the entire simulation time. Events were padded, taking a reference time unit to create spread view of all occurring events for group-based diff mechanism. So the method that we used, we performed diff on the transaction logs to extract out aligned differences with context. We then fed it to the Siamese model to produce an embedding of 1 cross 100 dimension in sample batches. Clustering algorithm was then applied to form groups, and we then dumped them in the form of text. So on evaluating, we found basically the groups were created with respect to the transaction logs, the absence of context, although in the simulation data and the dynamic time factor reduced the expected accuracy and usability. So the limitations: absence of good context with respect to the simulation data, the usage of context for transactions, dependency on availability of transaction informations, that is the initial assumptions that we took, lack of a GUI interface to see the exact difference in the running wave, inclusion of time factor in a more dynamic way to align groups. Coming to the conclusion with both the experiments, we have been able to handle text-based regression automation with our approach to a good and useful extent by classifying the diffs into defined groups and validating them to either accept or reject the changes, verifying and validation of changes in design with the available simulation data and the VCT files by grouping the occurring changes have been handled to a certain extent, reducing a little time effort or effort to verify waveforms, especially where there are no self-checking tests. Thank you.